Thank you for the invitation to speak today. This is going to be a lot more technical than previous talks, so I apologize in advance. Language modeling is the effort to build statistical models of text, and the main goal is to estimate the probability of strings. So typically what we actually want to estimate is the probability of an entire string parameterized by some kind of model theta. And this is intractable for most strings because we just have too many possibilities to enumerate. As we know from 1948 onwards, we can decompose this using simple things like Markov chain assumptions. In this case here, this is a bigram Markov chain, which says we could estimate the probability of the next word in the sequence just given the previous word. What we actually do now with neural networks is condition it on much more information. And you might be wondering, well, why is this useful? It's at the heart of everything that we're talking about today. It's useful for spell checking and grammar checking. It's used in machine translation. If you've used Google Translate, if you've used ChatGPT, it's also the backbone of this. It's used for topic modeling and text prediction. It's really everywhere. And if I had to summarize the status of the field, it's scale. If we look along the axes here, everything in this area has moved towards training larger models, so that's moving into the billions and hundreds of billions of parameters on hundreds of millions, billions, or even trillions of input tokens. And you've probably heard of some of these models like GPT or Llama. And so one of the questions that we ask here at the University of Copenhagen is, what's left? And for us, it's developing natural language processing for all languages. There are about 7,000 languages in the world, of which 3,000 are written. And there's more than 400 languages with 1 million speakers. And natural language processing models typically only support 100 languages, which gives technological exclusion for billions of people. If we look at this chart here, if you are a speaker of Mandarin or English or Spanish, you're okay. If you speak Danish, you're already well down the curve. And if you go down to languages like Faroese or Basque, you have so few speakers of your language and so few resources that it's actually quite difficult to imagine these models being useful for you. And maybe you have this experience yourself interacting with your mobile phone or with a translation system. So what's the main challenge here? It's that language models have a discrete input and output vocabulary that's expressed over what we call tokens, characters, words, or subwords. And this creates bottlenecks. It creates them in the input layer. I don't know why these slides are inverted color, I apologize. So at the bottom of this here, we have a representational bottleneck where we're trying to input words down here in the embedding layer. And there's also a computational bottleneck at the output layer where we're trying to predict the next words in a sequence. Why is this a challenge? It's because natural language processing follows a pipeline. So we'll start with a piece of raw text, like this sentence about Kikuko, and from there we would normalize this. One common thing might be we'd split the punctuation off from the surrounding words. Then we would use some kind of tokenizer to split words into subwords. In this instance, if we have an English tokenizer, it will have seen this Danish word so few times that it will produce an unusual split of the input text. This would never happen if the model was trained on Danish text. The remainder of the sentence is fine. These are then associated with real value vectors, which are much longer than these trivial examples I'm showing here. And this is the input to a neural network like BERT or GPT or Llama, upon which we perform syntactic or semantic analysis. What I'm going to talk to you about today is an approach that we call visual language modeling, where we've been taking this traditional pipeline and throwing everything away, and instead replacing it with one simple step, which is to render text as images. And what this means is that any sentence and any writing system that we can handle through our font renderer can be rendered into an image like the one shown here. This is an example in English. We also have an example below in Amharic, which is a language from Eastern Africa. And we call this pixel-based language modeling. So the way this works is we take a text collection from a hard disk or maybe from a Hugging Face data set, and we use something called Panga Cairo to render this text into an image using the open source Google Noto fonts. Our images are 16 by 16 patches, and we just draw the text directly into there in full RGB space. The patches are then embedded by a simple convolutional neural network layer. We then randomly mask some of these image patches so the model does not see them. And then this is processed through what's called a transformer encoder, which is a 12-layer neural network. And then there's a transformer decoder on the other side that's trying to predict pixel by pixel what was missing in the masked patches down at the bottom in the input. And so no part of this model really knows what words are. It's pixels in, pixels out. The text renderer that we've developed is super flexible. It can handle full RGB colors. It can deal with rendering emojis. It can also deal with left to right writing systems and right to left writing systems, so Chinese and Arabic here in these examples. We can also render words instead of just continuous streams as well, as shown here in Amharic. And one of the first things we get out of this approach is a new type of generative model of language. So what I'm showing you here is the progression of the reconstructions this model makes as we train it for 100,000 parameter updates up to 1 million on the other side. The gray areas are the parts the model is trying to reconstruct at the pixel level. This is an article about penguins and how they have hydrodynamic body structures based on their knees. The student that led this project thought it was a good example because the model had never seen it. And so if we look here, going from your left to right, that examples highlighted in blue shows really good progressions the model makes as it learns. We can see here on the bottom one, the first example is complete nonsense. In the middle, it generates a non-word, the word clusion. I don't know this word, but it likes it. And at the end, it generates illusion correctly, given the space available to it. It doesn't always succeed, though. Some reconstructions are beyond this model at the pixel level, even after 1 million parameter updates. This is a cherry-picked example. I can also take the announcement of this event, which it has never seen. It struggles with reconstructing proper names, so Daniel Spicol is not really there at all in the right-hand side. It struggles a lot with long gaps where it has to reconstruct things, and also dates and times. So it's very uncertain, this area in green, about when events were happening. It thinks it's maybe 1730, 1930. It's a bit unsure. But one of the benefits I want to highlight here is that this model can process any text that can be rendered. It's not specialized to high-resource languages. And it can also potentially support previously written text, perhaps in national archives, maybe the letters of the Danish library, maybe maps, all types of visual data that's existed before the existence of the internet. For some more technical details, which I'm sure you want, we train this model on 2 English data sets. One is Wikipedia, and one is a large collection of books. We train it for 8 days on 8 GPUs using Euro HPC computing power. And our model is really small. It has 86 million parameters in the encoder. When you compare that against something like GPT-3, which has 175 billion, you can see we're working at a different scale. Our model has probably seen about 0.05% of non-English text. So it really doesn't know anything about other languages from its pre-training. And an example of the type of non-English text it would see, in this article about the Great Wall of China, you may have a sequence of Chinese symbols that tell you what that is in traditional Chinese. And this is not enough to learn Chinese language. Not even in the Chinese rune argument from Searle could you argue about this. In terms of how we use this in our research, we've been applying this to tasks like language parsing, where we want to predict the syntactic relationships between words and sentences. The y-axis here shows a performance measure, F-score. The x-axis shows different languages, English on this side, and Chinese here over on the far side. And one of the things that's really exciting for us was that on scripts that the model has not seen, it vastly outperforms a model trained on exactly the same data. This model is called BERT from 2018. So this was a super exciting development for us. We also applied it to other tasks like named entity recognition. This is a named entity recognition in a collection of African languages. One thing that's really exciting again is that this Amharic script, our model outperforms the other models. One of them is BERT, another is a multilingual Canine model from Google Research. And something that's really great is that our model outperforms Canine, which is pre-trained on multilingual text. Our model has only seen English text, which we think is an exciting development for these types of small, compact models that you can train in universities. The model can also adapt to new fonts. This is an example of taking our original font, adapting it to a font with serifs, or going all in and using dingbats, which I'm sure you've played with in your text editor and you think, this is crazy. Our model doesn't think it's that crazy. It's willing to process these as if it's actually the sentence, my cat loves oatmeal and pancakes. And I think this is a crucial step towards adapting these models to deal with handwritten text or scanned text from newspapers or other sources. We've been continuing to work on this idea since the middle of last year. One of our current questions is what type of data actually matters here. And we're looking at the full spectrum. One side, we have images which have no linguistic grammar at all. This is just RGB data of cats and dogs and houses. We can have collections of equations rendered in math tech using basic algebra. We also look at things like Python code or other programming languages which have LLK grammars. And then on the side here, we have full natural language from things like Wikipedia. What we know is that it is very important to train this model that knows nothing about language beyond pixels on actual natural language data. But that if you have code and you also have doc strings, you can get very far. And it turns out that all this documentation that you may be writing as part of your jobs, or that you wrote in the past in your jobs, is useful for many things. And so you didn't know it, but it was. The model is available for you to try yourselves. If you have your phone, you can scan this QR code. This model is only pre-trained on English text. If you enter Danish text, it will produce absolute nonsense. We do have some multilingual versions of the model that we're developing now, but we're not yet ready to show them for other people. So I'd like to conclude my talk. I've been trying to convince you that we're doing some exciting research on this idea of pixel-based language modeling. We're trying to tackle what we call the open vocabulary problem using visually rendered text instead of discrete tokens. My opinion is that language is a really special thing that enables human communication, but its computer representation should be as flexible and as expressive as possible. We realize this through pixel renderings, but we don't think this is the end of the story. I'd also like to finish by thanking the Velum Foundation for their generous support of the work.